I want to talk about how to measure Z in and Z out in the labs, specifically labs 5 and 6. So this is actually covered in the notes, the analysis of transistor amps, and I think maybe the videos, but I thought I'd make one just for this. So this is how to do it in the real world or virtually in MultiSim. So the section that's of interest is this one on the input impedance of a transistor. And the basic method is to inject a current into an unknown impedance and measure the voltage that develops across it. And by knowing what the current is and the voltage is, you can figure out what Zin is by V over I. So how do you do that in MultiSim? Well, let's take a look at this circuit. So I've got a two-port model here, because when we do our analysis of our schematic with our transistor in it, what we're doing is we're reducing it down to a two-port model. So in my two-port model here, I have a Zin with no value given and a Zout with no value, and then a dependent source, which is some multiple of what comes in. So how do I figure out what Zin is in MultiSim? Okay, so what you would do in MultiSim is you want to add a function generator. So I've got a function generator here. And what you're going to want to do is you're going to want to inject a signal into the circuit in order to measure the Zin. But we don't want to go straight into the circuit. We want to go into the circuit through a current source. And so using the current source, we can measure what the current is that it's going into the circuit, that's going into the amplifier over here. And then what I'm going to do is I'm going to add a second meter here, which is a voltmeter. And using a voltmeter, I'm going to measure the voltage that is across the input of the circuit. So I'll start the simulation here. So the simulation's running, and what I've got here is I'm measuring that 10 volts is the voltage that is appearing across the input or across Zin, and the current is going in is about 10 milliamps. And 10 over 10, 10 volts over 10 milliamps would give you a Zin of 1K. So by injecting a signal and measuring the voltage and current, I can figure out what Zin is. And if I double click on this and bring it up, you can actually see that that part is 1K in value. So that's how we do Zin. Let's drop this one into whiteboard in order to figure out what Zin is. So over here, we can see that on this meter here, that we've applied 10 volts to the input. And over here, we can see that we have 10 milliamps of current going into the circuit and 10 volts across it. Therefore, Zin, it has 10 volts across it, and basically 10 milliamps flows into it. Zin equals 1K ohm. Where now I want to figure out what Zout is based on measured values. So what do you do to measure Zout? Well, what you do is you put a load onto the output side of this amplifier, and you put a little switch in it here. So what we're going to do is we got a load there. I'm going to pop up this meter, run the simulation. So what's happening is I'm measuring 1,000 millivolts coming out of this amplifier circuit, and that's with the switch open. So this is the open circuit voltage. And since the circuit is open, it means that if I'm measuring 1 volt here, that's the voltage of this source. So I know what the open circuit voltage is. And then if I close this circuit, you can see that it drops down a little bit. It drops down to 500 millivolts. This is the loaded voltage. And by knowing the open circuit voltage and the loaded voltage and the value of this resistance, I can figure out what Zout is. The other thing that I can do at this point here is I could just stop the simulation here for a second, and I could inject another meter here. So I want to measure the amps. I want to measure the current going into the load, run the simulation. First, I'll start with it open. So I'm running the simulation, and you can see it says it's 10 nanoamps. It's a little bit of an error because in reality, if it's open circuit, it's going to be 0 amps, period. But 10 nanoamps is effectively 0, and I have 1 volt here. So we can see that this is the open circuit voltage. And then when I close this switch, I can see that I'm getting 500 microamps, and that's 0.5 milliamps. So by knowing the current going to the load, I can work back and I say, oh, that's also the current going through Zout. And by knowing the voltage on the load, I could say, oh, well, if this is 1 volt and that's a half a volt, then this has a half a volt across it. And therefore I know the voltage across this, and I know the current through it. I can now figure out what Zout is. Let's drop that into whiteboard to do the calculations of Zout. So here's the amplifier output, and we're measuring the output voltage here with this meter, and it says it's 500 millivolts, 0.5 volts. So let's write that in, 500 millivolts. This one over here is measuring the current, and that is 500 microamps, which is 0.5 milliamps. So the current is going through this way, 0.5 milliamps. So that is the current, then we know that that current goes through here. It's 0.5 milliamps, and we had dialed in that this is 1 volt RMS, and therefore the voltage across this guy, if I've got 500 millivolts here, that means I've got the other 500 millivolts here. So Zout has 500 millivolts across it, and it has 0.5 milliamps through it. That is 1 k ohm. In part 4 of the lab, you're going to do a frequency response measurement of the 2-stage amplifier. And you're going to do this by injecting a signal at a variety of frequencies from 50 hertz up to 100,000 hertz. And you're going to measure the gain at each of those frequencies of the signal, and you're going to plot it on a graph. And this is a frequency response graph. So if you take a look at this graph, along the horizontal axis you have frequency, and you'll notice that this is a logarithmic scale. So this is 10, and it's pretty wide space between there to the next tick. This is 20, 30, 40, 50, 60, 70, 80, 90, 100. As the frequency goes up, the space between the tick marks goes down. So what they're doing is they are allocating less space in the graph to the high frequencies and more space to the low frequencies. And this will bring out details that happen at lower frequencies. And then on the vertical axis, you're going to plot the actual gain value that you measure at each of those frequencies. So this is what you're going to do. How do I do that in MultiSim? So how I would do that in MultiSim is I would take a function generator and I'd apply it to the input of stage 1, and I would let the signal ripple through and come out on stage 2. And I would inject the signal and monitor input and output with the scope at the same time. So let's start the simulation. Right now I'm going to start at about 10 kilohertz and about 1 volt peak. Let's see what happens. So the simulation is running. I'm going to bring up the scope. And when I look at 1 volt peak and 10 kilohertz, I can see a nice sine wave going in, but the output has these flat spots on them. And the problem here is that I'm injecting a signal that is big enough to cause the output to go between saturation and cutoff. So the input signal is too big. You cannot measure gain when you have these flat spots. And the reason you can't do that is because it actually wants to go higher. So you cannot compare the peak-to-peak input to the peak-to-peak output because it's not reaching that peak. So in order for this to work, you're going to have to reduce the input voltage until you get a sine wave on the input and the output. And you cannot measure gain properly unless you have a good output. If you got garbage coming out, then you're not doing a proper gain measurement. Now, one of the things I'm going to say, though, is that I've put in 0.1 volts peak here just to show you how it works. But here's a little trick that I've used. If I use a 0.1414, if If I use 0.1414 volts peak, that will be exactly 1 volt RMS, or 0.1 volts RMS. And if I apply that into the input, here I'll just do the measure. I'll have to start the scope over here to get this to run. You can see that I'm applying exactly 100 millivolts into the input. If I use a nice round number, I don't have to pull the calculator out every time to figure out what gain is. This is 0.1 millivolts AC RMS going onto the input, and if I put a meter on the output here, I'll hook a meter up to the output, and I'm going to have to so now you can see that the output is 1.66 volts RMS out, 0.1 in. The gain then at 10 kilohertz is 16.7. And I could enter that number into my graph. So if you use 0.1414 and you multiply it by root 2, that's 100 millivolts AC RMS, you can use the AC voltmeters to very quickly measure the input and output voltage and then calculate gain just by shifting the decimal point. So I said 10 kilohertz. I think we said 10 kilohertz. At 10 kilohertz, we're putting 100 millivolts in. Got out 1.667 volts. That's a gain of 16.7. And what I would do is I would put that on my graph right down here. And then I could go to a different point. Let's say 1 kilohertz. So now it's at 1 kilohertz. Now you'll note that I have not changed the peak amplitude at all. I just changed the frequency in the input. So I'm still inputting 0.1 volts RMS. Now I got 880 millivolts out. That gain is 8.8. And I can mark that point in my graph. Now you will notice that as you get lower on frequency, so if I go 100 hertz, for example, it will be a very small output. In fact, the output is actually lower than what's coming in. This is because the capacitors are going open circuit and I'm no longer getting a signal through it. Actually, it's higher right now, but if I go down, let's say to 10 hertz, now you can see I've almost got nothing out. So it usually helps when you're doing something like this to start in the middle, to figure out where the sweet spot is or where it amplifies very well, and adjust your input output. And then you can very quickly sweep through the input circuits, write down what the gains are, and then plot your response. And I've kind of done that ahead of time here, with cheated a little bit. So basically at 50 hertz, the gain was 0.81, 2.32 times bigger, 5.6. And what I've done is I've plotted these points on the graph. And then what you should do is you should join those points. You should join those points with a line. And you should get something that looks like this. And there is a little bit of a jog in here. You should keep that in mind. You should get something that looks like that. And if you do it very carefully, the line should go through all the points. So this is what you're expecting to get, and you are expecting a little bit of a jog here. I have a video on the frequency effects that the capacitors have. If you watch that one, you'll see what happens, why this is here, and what happens when you change some of the components.